These are the homework solutions for the force problems that I've assigned. They're due November 20th, and as I said, I think you need to look at these pretty well. So we'll try this with a screencast first and see how that goes. The first set is from Newton's Laws of Motion on the physics classroom calculator pad. The second part is from Vectors and Forces in Two Dimensions, that problem set. So for P1 here, this is just simply asking about the weight. So you need to understand that weight is measured in newtons, it is a force. Mass is measured in kilograms, it is not a force, it is the amount of matter in a substance. So this and force, any force are both measured in newtons, this is in kilograms. So the standard units. This is the conversion factor on Earth, which is 9.8 newtons per kilogram, which is equivalent to 9.8 meters per second squared. So for A, the elephant is 58,800 newtons on Earth. For B, on the moon, which has 1/6 the gravitational force, same mass, only 9,800 newtons. For problem 6, this is simply a Newton's second law equation. The key thing here is that it says that the person has a mass of 82 kilograms and the G-Whiz, which is that little rocket sled they were on, also has 82 kilograms, so the total mass is 164 kilograms. Often when I show you this equation, I put m tot here. That reminds me I need to think of the total mass that's accelerating. So 73,800 newtons. I've also given suggestions to draw lots of free body diagrams. So for number 14, this is an example. So I've got a normal force upward, a gravitational force downward, an applied force by Alex Perez, congratulations Alex, and a frictional force. It didn't say that the force was applied at an angle, so to make my life simple, I'm going to assume that it's not. So first thing I have to do, after drawing this, if I want to find the mass, is to take the weight of Alex and the sled, divide it by, or pardon me, Alex's brother and the sled, and divide it by 9.8 newtons per kilogram. And that gets me 31 kilograms. I was told that the frictional force or the resistive force is 24 newtons, the applied force 52. So then the net force is 28 newtons. Acceleration is net force over mass, and that's 0.9 meters per second squared. For number 17, this case was asking about air resistance. And so you have someone of mass 82.5 kilograms with a resistive force of 118 newtons. And you need to figure out the acceleration at that instant. So again, find out the weight, which is the same as the gravitational force, m times g, 808.5 newtons. So in this case, the net force is gravitational force minus the force of the air, since they're acting in different directions. Probably should have drawn a free body diagram for that also, and divided by the mass. So 808.5 minus 118 over 82.5. As time goes on and the person falls faster and faster, the force of the Earth is not going to significantly change, but the force of the air is significantly going to change, up until the point where the force of the air up is equal to the force of gravity down. And at that time, the person will be at terminal velocity, which is 0 meters per second squared. For P21, this is actually one where, again, I think the free body diagram is extremely helpful. It says a 0.104 kilogram rocket accelerates upward at a certain rate. It was 45.9 meters per second squared, and you're asked to find the thrust. So the key thing here is that thrust is pushing the rocket upward, gravity is pulling it downward. So the acceleration that was given is once again equal to the net force over the mass. So the gravitational force on the rocket is 1.02 newtons. You have to recognize that's acting against the thrust. So acceleration 45.9 is equal to thrust minus that gravitational force over the mass. The thrust is 5.79 newtons. If you didn't take the gravitational force into account, you're going to think the thrust is somewhat less, and that would result in a lower acceleration. So again, take a look at this one very carefully. P26, this is, again, a problem with Newton's second law, also involves coefficient of friction. So we've got a normal force up, a gravitational force down, push to the right, friction to the left. So the mass that's moving is 84 kilograms. The acceleration is 1.2 meters per second squared. I'm going to find the weight of the object, which is m times g. It's 823.2 newtons. The normal force would also be 823.2 newtons. Those two factors are going to help me find the force of friction, since the coefficient of friction is equal to frictional force over normal force. So the frictional force is around 288 newtons. And now I've got to put together the pieces to find the acceleration. So the upward and downward forces balance out, the horizontal forces don't. So the push minus friction is equal to m times a. So this is a revised version of Newton's second law. Now really I should put m tote here. I neglected to do that. So the push minus 288 equal to the mass times that acceleration. The push is 389 newtons. So again, that's a good one to look over. For P2 and P6, P2 is simply splitting up a vector that's at an angle into the horizontal and vertical components. That should be very straightforward by now. P6, I'm going to set up a T-chart as I've asked you to do before. That's going to help you get the net force. So I end up with a net force of 174 newtons east and 76 newtons south, actually. This one, which is the force going to the northeast, I had to split into components using trig. Notice I'm showing you my work for that, as you should show for me. At that point, once I have these two components, I'm going to reassemble them for vector resolution purposes. I'm going to get a resultant that's 190 newtons at 23.6 degrees south of east. You could also have gotten somewhere around 64.4 degrees east of south. So to find the acceleration, I'm going to go back to Newton's second law, net force over mass. 190 newtons over the carcass, which had 750 kilograms of mass. So that's 0.25 meters per second squared, and that's in the same direction as the net force. Acceleration is always in the same direction as net force. That's something that's important to remember. And it's described by Newton's second law. So for number 9, in this particular case, this I think is one of the toughest problems. So here's a free body diagram. We've got a mass of an object, 112 kilograms, has a gravitational force downward, so that's m times g again, 1098 newtons. We've got a frictional force acting to the left the way that I've drawn it. Don't know how much that is. We've got an applied force acting up and to the right, and then a normal force upward. Notice that the normal force is not equal to the gravitational force because of this upward force. So the fact that the object is being pulled up and at an angle, it was not mentioned that the object is like leaving the ground. So that just tells us that this upward component of this is less than the gravitational force down. So there's still some force of the floor upward. So there's a lot going on. So the vertical component of that I'm going to figure out is 407 newtons up. The horizontal component is 560 newtons to the right. And so therefore, I can find the normal force by saying that the normal force plus the applied vertical component upward would equal the gravitational force downward. So since the upward component is 407 newtons, that leaves 691 newtons for the normal force. I can use that to find the frictional force. Mu times F normal is 379 newtons. So now I can find the acceleration by doing applied horizontal force minus the frictional force. Why just the horizontal component? Because the vertical forces do balance. The normal force up plus the vertical component of the applied force up are equal to gravitational force down, but the horizontal components do not necessarily balance. And in fact, when I plug this in, I get 379 newtons of frictional force. That's less than the horizontal component of the applied force. So, I screwed up. Okay, so I am going to have to figure that to correct this at this point. So I'm going to say that is going to be 560 newtons. I like that I did this. Not that I screwed up, but that I could figure that out. minus 379 newtons, and that's going to give me a different acceleration. So hold on to that. So as you can tell, it's pretty easy to have that happen. So the net force 560 minus 379, 181 divided by 112 kilograms, 1.62 or 1.6 meters per second squared. So I'm going to have another one here. 0.6. So I'll do this and this. Put that over here. Okay, I think that's correct. Wow, what a fix. Okay, and so then for number 13, which is the last one, I'm going to end up having force up is equal to force down. So in this case, the upward force is the vertical component of both these tensions. The downward force is equal to the weight of this, so that's M times G, 422 newtons. I did a sample similar to this in class, and so the tension in each cable is 373 newtons. If this angle changes, the tension will change. A more vertical angle will cause less tension in each cable. A more horizontal angle will cause more tension in each cable. So glad I caught that mistake, and hopefully there's no others. If so, we'll go over them in class.